Good evening once again. Today we are supposed to discuss some ideas from elementary number theory. So elementary number theory, it's as all of us know that it's one of the oldest branches of mathematics where people are mainly interested in the properties of integers especially, and of course number theory is not entirely related to integers. It's something very close to the set of all rational numbers, and it can go to several other different fields like periodic numbers, etc. But here we will be trying to see some properties that are related to integers, natural numbers, and probably we will see that how to move from integers to these congruence rings and related stuff in abstract algebra. Okay, so let me start sharing the screen. I should give a name matching this thing. 16. Right. And let me share the Google worksheet link also. It's here. So the very first thing that we remember when we start understanding number theory is the concept of divisors, right? Divisors, that Euclidean algorithm, Euclid division algorithm is there first of all, and these related things are the major things that we initially think of. So probably we will start with divisors. For finding divisors, there is a built-in command called divisors itself. Let's try to see that first. So suppose that we initialize with a is equal to some number, say b is also equal to some 16, then divisors of a. We'll simply print all the divisors of a. Now, similarly, divisors of b will give the divisors of b. So we know that the GCD is nothing but the, we are supposed to take the divisors of a intersection divisors of b. These two are, okay, what type of objects these two are? Let us see that. Are they sets? They seems to be lists. They seems to be lists. It's a list. Maybe we can convert that into list. Sorry, a set. So let me just change it to div A, set of all divisors of A. Let us define it like this. Similarly, div B, set of all divisors of B. So if we ask for div A, div B, we will get both the sets. Okay, now we can take the intersection. Common div. So simply take the intersection of these two. Intersection, and I think and also we would have used, maybe we can even do that. Div B, common divisors. These are the common divisors. Now take the largest That's a GCD. This is the direct method, definition method for finding the GCD. Of course, we can, there is already a built-in command available. I will come to that. Maximum of common divisors. That's it. And the direct method is not necessary to do any of these things. GCD A, B. This is a direct method. But as I told yesterday itself, if we straight away go into direct method, we will not find these commands interesting. We need actually a problem to demonstrate how to, why to use these commands, divisors, taking the intersection, all these things. I'm just using this long route to show you that what are the possible commands available in SageMath and how they can be actually employed to solve certain specific problems. That's it. So the purpose of this program is not actually to find out, not actually to write a program to find GCD, but to just demonstrate the commands available in SageMath and how to make use of these things in some problems. Okay, so that's it. I'm updating the Google Sheet, Google document with this. The Google document is now updated. So GCD using definition means that by the definition GCD is nothing but it's the greatest common divisor. Therefore, divisors we have to find first, common divisors we have to find next, and from that we have to take the greatest. That's what we have done, maximum. So divisors found, common intersection taken, and then the maximum taken. This is the definition of GCD. Now there are different ways to find out GCD. So we will discuss each of them, and each and every time trying to introduce at least one new command. Now the division theorem, we are all familiar with the division theorem. It says that whenever b is a positive integer, we can write a is equal to bq plus r, where q is the quotient and r is the remainder. Okay, so finding a is equal to bq plus r so writing a is equal to bq plus r is easy. But now if you want to write down all the steps in the finding the GCD, okay, suppose that we want to find all the steps in GCD and the steps involved in finding the GCD using Euclidean algorithm. All these purposes are for pedagogical, what do you call it? These are all pedagogical purposes, because GCD finding is really easy using the GCD command itself. But suppose that we want to demonstrate how the Euclidean algorithm is working, suppose that we want to see all the steps in between. So how do we do that? That's what we want to see. So each and every step we have to take a is equal to bq plus r. That's what in Euclidean algorithm we do. So Euclidean algorithm. Next problem is a demonstration. Means that in the Euclidean algorithm, remember that the steps we follow is we write a is equal to bq plus r first. After that we interchange, we replace a with b and b with r, and we continue this process until the remainder becomes 0. So the last non-zero remainder we take as the GCD. So to do that, we have to do all these things in a loop. We need to print out all the things, right? So let us take a and b to be exactly the same thing. A and b is this. Now what are we supposed to print? What are the things that we have to print? A is equal to bq plus r is what we need. So a, let us use equal to. The equal to sign also if we want, then we need to enclose it in equal to. A equal to, what is b, what is q? B is quite known to us, b is already given to us. B, now let us put an into mark, star mark. BQ. How do we find Q? What is actually Q? Q is nothing but, remember that Q is nothing but Q is A by B and the floor of that. Okay, the greatest integer not exceeding. This Q is the greatest integer not exceeding A. Okay, that's one way. And the other way probably is that we need to take this R from, we need to take this what you call B from A as many times as possible. Okay, but instead of that we can directly rely on this floor function. Floor of A by B. This is the greatest integer not exceeding. This is the quotient. Greatest integer not exceeding A by B. Floor of A by B. Sorry. A by B. B star. This is Q. And what is the remainder? Remainder is nothing but, we know that this is A we are dividing with B and the remainder we need. Therefore, A percentage B is the remainder. A percentage B. Let us see the output of this. Oh, one plus is missing. Okay. So what is the next step that we are supposed to do? In the next step, we are supposed to replace B with A and A with B and B with R. Okay, where R is A percentage B. Next step, B A. A B. A and B we replace with B A percentage B. Be careful about the order in which we are writing it. A, B. So, according to this, what will happen is the value B will be stored to A. Now, what about B? Now, B will be stored with the value A percentage B as the second step. Okay. The first step is A will be filled with the existing value of B. In the second step, B will be filled with A percentage B. Again, the same line, because we have just changed the values. A and B are still there. That's it. The remainder is 0. So the GCD is therefore equal to 8. Okay. So this is the these are the steps that we are supposed to follow. Now let us try to write it in a loop so that so whatever A, B we choose, we need not worry that how many steps we have to copy and paste. We don't have to worry about. We keep on checking whether A percentage becomes 0 or not. If it becomes 0, we stop, and last remainder we take as the GCD. Okay. Let me update. So the Google document is now updated. Now doing it in loop. So we want to continue this process until this A percentage B becomes 0. Okay. So let us do that. While A percentage B is not 0, we will keep on printing and interchanging. While A percentage B not equal to 0, what we will do? We will do this. We will interchange. That's it. And since A percentage B is not equal to 0, let us take R to be the remainder. Okay, so after this loop, what will happen is we will print GCD is, see that if A percentage B becomes 0, this R equal to A percentage B, this assignment will not take place. Therefore, R is equal to A plus B will take place only if this A percentage B is not equal to 0. Therefore, whatever non-zero remainders are there, that will be updated in this R. Therefore, from this while, the while loop will not be executed if A percentage B becomes 0. Therefore, R will not be assigned the value 0. R will be always having a non-zero value only. Okay, that's very important to understand. And not only that, it's better that it's possible that in the first step itself, R is 0. Therefore, in that case, if R is 0, there is one more extra things required, because if B is a divisor of A, R becomes 0. So we need to be really careful. If B divides A. How do we say B divides A? What is what's a technique for saying B divides A? One is that just ask if A percentage B is 0 or not. If A percentage B is equal to 0, then then what happens is B is a if A percentage B equal to 0, then A is a multiple of B. In that case, GCD is nothing but GCD is nothing but B itself. Okay, now else then only we need to go through all these steps. Let me just take it inside. That's it. Okay, let us see this in action. Oh, sorry, this R is not appearing here. So we can try with any number here, 276. $1,024. So all the steps are here. So now we can demonstrate the Euclidean algorithm to anyone using this. One thing is that I have not used anything from SageMath here. All these commands that we have used here are basically Python commands only. So the full the capability of Sage is not actually used here. All these functions are from the basic Python. So updating the Google document. Done. Okay. Now we will move to one fundamental identity or lemma in elementary number theory, which is known as Bezos identity. Or Bezos lemma, which essentially says that if D equal to GCD AB, there exists XY integers such that D equal to AX plus B1. This is what Bezos identity says. And usually the technique for finding this X and Y are known as Bezos coefficients usually. To find the Bezos coefficients, the technique is actually to take all the steps from the bottom upward. That means X plus 4 as a linear combination of 16 and 12. Then 12 is now a linear combination of 16 and 252. And 16 is a linear combination of 4 and 252 and 1024, and work backward. That's how we find the this X and Y. It's actually not very complicated, but the only thing is that when we are working backward, it's quite possible that we may in between try to simplify certain things which we are not actually supposed to simplify, because we want to get the final result in terms of 1276 and 1024. We should not lose that. So finding the Bezos identity coefficients in Sage is very easy, because already there is a built-in command. One more thing is, okay, I will show that first. So for finding the Bezos identity coefficients, the the stage command available is xgcd. Okay, it's not gcd, the command is xgcd. So suppose that we take these two numbers. So Bezos identity coefficient, suppose we call that to be BIC, xgcd of A and B. Let's print it. So 4 minus 65, 81. You should read it as 4 equal to minus 65 into A plus 81 into B. We can verify that if you want. Suppose we write D as the GCD and X and Y. Four minus 65. So we are unpacking them, and if you want to see what these values are, X star A plus Y star B, is it equal to D? The answer is true. That means AX plus BY or A star X plus B star Y, both are the same. So this is the way to find the Bezos identity coefficients. So why is this useful? What is the purpose of doing all these things? Because Bezos identity is used for solving linear Diophantine equations in two variables. So for example, suppose that we have the equation C is equal to X plus B. Suppose that we want to solve C is equal to X plus BY. So solving linear equation C equal to AX plus BY. So a solution for AX plus BY is equal to CX is provided that the GCD of A and B divides C. So the very first thing that we have to check is if this is true or not. Okay, the GCD is equal to GCD is C is a multiple of D or not. That's the very first thing that we have to check. For example, suppose that we take the GCD here is 4. So let us take C to be equal to 20, for example. C equal to 20. So we want. So we now know what exactly we are supposed to do, because if we take C to be equal to 20, we already have 4 is equal to minus 65 into 1276 plus 81 into 1024. Therefore, if you multiply with 20 on both sides, you will be getting on the left side. Sorry, if you multiply with 5 on both sides, you will be getting on the left 20, and you multiply X and Y with this the same 5. So you will be getting a solution. So 5x and 5a are the actual solutions. Here 5x and 5a will be the solutions. So for that, the very first thing that we have to check is if C is a multiple of D or not. C percentage D not equal to 0. What we are supposed to print? The linear Diophantine is LD. Let us start it. The linear Diophantine equation, we actually want an integer solution for the equation AX plus BY is equal to C. And the integer solution X is provided that GCD of A and B divides C. So if the C percentage D is not equal to 0, we will simply say that this is not solvable. Otherwise, what is one solution? We can see that. So if we have 20 on the left side, now to get 20, what we are supposed to do from 4? So we are supposed to multiply AX plus BY is equal to D. We are supposed to multiply AX plus BY is equal to. So what is the step that we have to follow? So to find to solve c equal to ax plus by. We are supposed to multiply d equal to ax plus, okay, so this is a little bit confusing, therefore I will change the notation to dx naught and y naught, x naught, y naught, because otherwise we will be using the same symbol again and again. Multiply d is equal to ax naught plus by naught with what? With 20 by d or c by d. Okay, that's one solution. I think this is correct. If you are finding something, some issue with whatever I am saying, please just give me a warning that I am doing it wrong. I guess that is correct. Okay, let us multiply. So already we have x naught and y naught. So x naught, y naught is there. Therefore, a solution is, so we have to multiply. X naught is already there. X naught with c by d, y naught with c by d. This is correct, that we can check. Minus 325 into a. So verification. Uh, 20 equal to a star this plus b star this. Now we know that we can find the general solution also exactly using the same command. The set of all solutions is given by x naught minus b by d into t, y naught plus a by d into t. These are the general solutions, and we can give the general solution also. But we need to define in that case one variable t. X naught minus a by d. See that here essentially what we are taking is we are multiplying x naught, minus a by d into t plus y naught plus x naught minus b by d, right? I got it wrong. Y naught plus a by d star t. Updating the Google document. So I have updated the Google document with this. Maybe we can even put this as a list so that one comma also will be there. So if you put different values for t, for example, if you put t is equal to 0, you will be getting minus 65. If you put t is equal to 0, what will you get? Minus 65 and 81. Sorry, I'm missing something. So this is a solution for. Now I need to multiply with c by d, right? Because I'll be just solving this. See, if I put t is equal to 0, I'll be getting minus 65 and 81. That's actually the solution of d is equal to. So if I want a solution for c is equal to, I need to multiply with c by d, right? So I need to multiply with c by d. This is correct now. When t is equal to 0, we get minus 325. When t is equal to 0, we get 405. Yeah, that's correct. So for getting the general solution, we are supposed to take x naught minus b by d into t, y naught plus a by d into t, which is the general solution for the equation d is equal to ax plus by, but we actually want c is equal to x plus dy, where d divides c. Therefore, we need to account for that extra factor c by d. So we get the final general solution of the linear differential equation. Ax plus by is equal to c to be this. This is the general solution. Means for various values of t, you will be getting different possibilities. Let me just revise the Google document. Done. Okay, so let us now try to do some more problems. Remember that finding this what you call number of less than or equal to lately prime. So remember that GCD can be found using the GCD command. Therefore, LCM also can be found using, as we can easily guess that LCM using the LCM command, and the usual. A very well known result. So let us take A and B here. Is that LCM into GCD is nothing but it's equal to the product of the two numbers. Let us try to see if this is true. LCM AB star GCD AB. Now A star B. What is the result? They are equal. Now, how do we define the Euler-Torsion function? We are very familiar with the Euler-Torsion function, phi of n. Phi of n, we know that it gives the number of integers, number of positive integers less than or equal to the number and lately prime to it, right? So we can define phi of n using the GCD function, because if we see that the GCD is 1, so we essentially need the lately prime number. So we can define a GCD function to be the set of all the cardinality of the set of all numbers in the range 1 to n that are lately prime to n. That means GCD is 1. Okay, so maybe we can form a set relatively prime to n. Suppose that n is given, n equal to 20, relatively prime to n. The set is nothing but d in or m in the range m for m in the range 1 2 etc. n if GCD m n equal to 1. Okay, so we'll get the set of all the list of all numbers that are relatively prime to n. Let us see if this is working. So 1 3 7 9, okay, all the primes, because 20, yes. Now if you try with 27, what will you get? I think that's correct. Now what is phi? Phi of n we can define to be, so phi of n is, so what are we supposed to do here? Just take the number of elements in this set. LE, fine. Yeah, that's right. Phi n is this. Phi n is 80. So directly also we can do. But this is not actually a function, remember. Because if you have to define it as a function, we need to use the def command. Or otherwise, how can you do that? Can you do something like this? Phi of n equal to, I don't think so, because if you define it like that, no, this is not going to work. You may try, this is not going to work. Okay, this is one method. Another method is that we know the formula that phi of n is equal to nothing but n into all primes divided, right? N into the product of all, the set of n times product of all 1 minus 1 by p, where p is a prime divisor of it. But for that we need to find out the prime divisors. Now how do we find prime divisors? That's another definition. This is here. Okay, let me update the Google document with this. LCM GCD done. Sorry. Now the prime divisor. So prime divisors, as we can probably guess, that the formula for the command for prime divisors is just prime divisors. That's true. So for defining phi n, just take the product. So n star product of list of all 1 minus 1 by p. Maybe a bracket we can put for p in prime divisors of n. That's it. See that this is the way in which we usually write mathematics. N star product of 1 minus 1 by p Instead of 4 in mathematics, we write below that product notation where we read it as where P belongs to the set of all prime divisors. P belongs to P is a prime and P divides N. That's what we usually write. But instead of that, we simply write P in prime divisors of N. That's it. So in both these ways, we can define the Euler phi function, torsion function. But Sage being a mathematics software, there is already a built-in method available for doing all these things. So we don't have to write these things. But what did I tell all these commands is that because otherwise, how do we feel that these commands are actually necessary, or what is the purpose of these commands? That's it. Euler phi. That's what the function name is. Instead of doing all these things. That's it. Okay. Now another function available in the elementary number theory is the sum of all divisors. Sum of all divisors, as we can see that the sigma function, which is what we usually call sum of divisors. Suppose that n is equal to 100. So sum divisors, we can take it to be equal to sum and then divisor, right? D for D in divisors of n. It's 217. Maybe we can try with 10. So 2, 1, 2, 5, 10. So 7 plus 8, 18. What about sum of squares of the divisors? Call it as square. Just take d square. But as I already told, Sage being a mathematics software, there are built-in functions. Sum of sigma n2, which means that sum of squares. Sigma n1 means sum of divisors. So this is the function. Sigma n power. Which power? And in fact, this is nothing but sigma 2 of n in the number theory notation. So updating the Google document. Done.
Sir, here is that phi of n, that is the sum of divisors. Is the phi function is there also?
Sorry?
The phi function is that sum of the divisor.
Phi of n is not sum of divisors. Phi of n is the number of numbers less than n relatively prime to n.
Okay.
So for example, if you take 4, phi of 4 is, you need to count the numbers less than that relatively prime to it. Therefore 1 and 3 you need to count. So it's 2.
Okay.
So like that. So sum
Oh,
5. Sorry?
1 and 3, that is sum of these 4.
No. 1 and 3 are the numbers that are relatively prime to 4. So their count, that's what phi of n gives.
Or their count.
Yeah, it's a counting function. It's not a summing function. Euler torsion function is a counting function, whereas sigma is a summing function. Yeah, that's why that name sigma, because sigma usually we use for sum. Phi, there is no summation. Okay, there are several other functions in just like to check if a number is actually a square or not. So n equal to 100. Is square n. Yes, n is a square. N is not a square. Second is n square free, means that a square free integer is one which has no square divisors, no square factors. Because 150, we know that 25 is there. 25 is a square. 25 divides 150. So 24, that's also not square free. 10, that's square free because no square divides it. Other than, of course, by square free we mean that no squares other than 1 square, because 1 square definitely divides a number. No square other than 1 square divides that number. That's what square free is. These two are some other functions. There are several other functions like the usual Mobius function, almost all kinds of number theory. So what do you call it? Number theoretic functions are available here. Arithmetical functions, which are usually called as. Now we will go into some more prime number related theory. So we have already seen the divisors we can find. Okay, divisors of A we can find. 1, 2, 7, 6, some number we have taken. Print. Divisors of A we can like this. Maybe we'll take a small number. 1, 2, 3, 4, etc. But here, okay. So how do we factorize this A? So factorizing A. So because we know that 1, 2, 3, 4, 1, 2, 3, 4, 6, 8, 12, 4, 24, they are all divisors or factors of A. But factorization essentially means that we are supposed to write it as a product of these factors. Okay, factor. So this is prime factorization. Or sometimes we call it as. So we essentially mean that we are that 2 is appearing 3 times and 3 is appearing once. And if you use this, so here we get it as a list, which essentially means that 2 is appearing thrice. If you use print list factor A, 2 is appearing thrice and 3 is appearing once. primes and multiplicities. Yes.
So there's a factor, sir, that prime factorization theorem.
Sorry.
So it is like prime factorization theorem. Factors is giving the power prime number that and its power.
No. Prime factorization essentially says that any number can be written as a product of primes. That's a fundamental theorem of arithmetic, right?
So
And
can be written as a prime or power to the prime?
no, here we are writing it as a power of primes, 2 to the power 3 into 3. Factorization essentially means that by factor we mean the prime factorization, not definitely into some what you call arbitrary. Sorry, I didn't hear.
Means it's not that order defined way to write only that prime factor.
Yes, prime factorization only, because other factorization what we are supposed to do is that take a divisor. See, because otherwise how do Sage know that what type of factorization you want? Because 24 can be written as 2 into 12, that's one factorization, and 24 can be written as 3 into 8, that's another factorization. But which factorization you actually need, we don't know that, right? So from the prime factorization you can actually get all other factorizations, because see 2 to the power 3 into 3 to the power 1, that's what you have the prime factors. Okay, so if you vary any divisor is going to be of the form 2 to power something and 3 to power something of 24. In a divisor of 24 must be of the form 2 to power some number which is less than or equal to 3 and 3 to power some number which is less than or equal to 1. So once you get a divisor, you can write the other divisor also. So divide it with 24 and take the rest to be the other factor, if that is what you have in your mind. But if you want to list out all the 24 to be equal to all possible products, then you may have to write your own code, other than prime factorization if you want. So if you want 24 to be equal to 2 into 12 and then 3 into 8 and then 4 into 6, then you may have to write your own code. There is no other way. There is no built-in function, it seems. And here we can make explicitly we can show that which factor is appearing how many times using this same command. Because we have the multiplicity also, so just take 4 prime factor in, so we will simply print. So we can see that it's appearing like this. It's in a list 2, 3, where the first is actually the prime and second is the multiplicity. So PF prime, PF0 appears with multiplicity PF1. So prime 2 appears with multiplicity 3 and 3 appears with multiplicity 1. Because when we loop through this prime factor list, what happens is PF will initially assume this tuple 2, 3. So PF0 will be 2 and PF1 will be 3. PF0 will be 3 after that and PF1 will be this 1. So let me update the Google Sheet. I have not updated the square free things. Sum of divisors. Yeah, that's done. This is not done. So I have updated the Google document with this. And just to see how many prime factors are there, just take this 2 3 is considered as 1 and 3 1 is considered as second. Therefore, take the length of this prime factor list. Let me even print this. There are two prime factors of 24 or 4. Now there is actually a set called primes itself. There is a set called primes. So that set is defined by primes. That's it. We can ask, is A equal to 15? So, which is essentially asking A in P. The answer is false. The answer is true. So, the set of all primes is denoted by primes this symbol. So, to avoid using this repeatedly, we can simply assign it to a variable P. Small p or capital P, that doesn't matter. Or in fact, we don't have to even do this. You can simply ask, is prime A? That's also possible without even going to the set P. Is prime A? Is 11 prime? True. 19. 1023. False. There are several numbers of factors. There are several numbers of what do you call it? Prime related functions available in SageMath. Mainly because what I think is that number theory is one branch of mathematics where a lot of computations usually take place for understanding the theory behind that. Not only that, the developers of this SageMath software, I think many of them are famous number theorists. That's one reason probably. So another function is probably that prime range. So suppose that we want to get more prime functions. Prime range, suppose 1 to 100. So we get all the primes in the range 1 to 100. So this is equivalent to writing P. Remember that we have already defined P. Already assigned this P. We may simply write 1 to 100. I think 1 to 100 like this. Let us see. Or probably as a list. Oh, sorry. Here we are getting the first 100 primes. Here we are getting primes in the range 1 to 100. Here we are getting 100 primes. And if you go for the 10th prime to 100th prime or 20th prime, '31 is the 10th prime, and for 71 is probably 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 71 is the 10th prime. So if you want, okay, in fact this is equivalent to 1 to 100 is equivalent to actually writing primes first n. So suppose we want the first 100 primes, this is equivalent, these two are equivalent. 3 to 5, 41, 3 to, this is, I should have written 0 to. This is correct? 2 to 5, 41, 2 to 5, 41, because otherwise the first prime is P0. So if you specifically want nth prime, P10, it's a 10th prime, that's 31. So you can even do this. Now if you want number of primes up to 100, that's known as prime pi. Number of primes up to n. Let me update the Google document with all this. So update. Now there is one more function called the count function. So which essentially is analogous to this length function. So both seems to be more or less the same type of function. I don't see any major difference between these two. But count is more intuitive, right? It's more meaningful to us because count essentially means that count. But length is something that is not very a commonly used word in mathematics for the size of anything. Okay, one more thing is, okay, I'm not going to that. So we know that the primes essentially are in the form either 4n plus 1 or 4n plus 3, right? Because we know that all the odd numbers can be categorized into either 4n plus 1 primes. On dividing any odd number, we know that every prime other than 2, they are all odd numbers. Therefore, if you divide an odd number with 4, the remainder is going to be either equal to 1 or 3. So primes can be categorized into either 4n plus 1 prime or 4n plus 3 prime. Okay, 4n plus 1 prime means that a prime in the form 4n plus 1. For example, the prime 5 5 is nothing but 4 into 1 plus 1. Therefore, it's a 4n plus 1 prime. On the other hand, 11 is a 4n plus 3 prime. 4 into 2 plus 3. And 3 is also a 4n plus 3 prime. N is equal to 0. So, there are 4n plus 1 primes and 4n plus 3 primes. Okay. So, there was an interesting problem. It's very old problem, and it goes back to the lifetime of Hardy. The Hardy is quite familiar to all of us because of the connection between the great Ramanujan and Hardy. The problem was that, so which primes are more? For example, if you count the number of primes, okay, I'll try to show that. That's an interesting problem actually. So suppose that we take n to be equal to 100. Suppose that we find prime mod prime 4 mod 1, and let us take P in capital P, where capital P is nothing but primes if P mod 4 equal to 1, okay, P in not just in P, say in P 100, the first 100, among the first 100, which primes are 4 mod 1, or sorry, 1 mod 4 in fact. I should have written 1 mod 4. I think that's the correct way to write. Oh, P4 I should have written. P4, P in P100. Okay, anyway, we have taken to be n. But this is not, okay, what was prime range, primes in the range? I think this is much better for us. We wanted the primes up to 100, not the first 100 primes. So these are the primes. Now, what about 3? So maybe we can see that we can count them. Okay, count we will. Count is not actually just counting the list, it's something else. There are and 3, there are 11, there are 13. So what about this number from 10 onwards? 1, 1 mod 4. Three mod 4. So now 3 mod 4 is more. Okay, up to 10, up to 100. 3 mod 4 is still more, up to 1000. 3 mod 4 is still more. One more 0. Let us suppress this primes list. We need only that count. Three mod 4 is still more. Maybe we'll try it one more 0. Or it's too large. Maybe it will definitely work. 3 mod 4 is still more, but they are very close. You can see that, right? So the interesting problem was that, this problem is actually known as a prime number race problem. So suppose that these two are two runners, right? Two athletes. The prime modulo 1 and prime modulo 3, they are both running for securing the first place. But the thing is that this is actually an infinite race. So the primes are infinite. Set is infinite. Therefore, there is a possibility that the race will continue forever. But now the question is that at a given point of time, can we definitely say that 3 mod 4 will be always ahead of 1 mod 4? That means there are more primes at any given point on the number line. The 3 mod 4 will be consisting of more primes, slightly at least. 1136 and 1125. When we consider up to 20,000, that's not actually a huge lead, but there is a lead. Okay, that's a question. And this question was actually settled by Hardy, I think, right? So whether 1 mod 4, 3 mod 4, if we consider them to be two athletes running for the first place, at any finite point on the number line, can we certainly say that 3 mod 4 will be always ahead of 1 mod 4? That's a question. Okay, prime number race. I think that's a problem name. Let me just copy and paste this. To the Google document. Sorted. Okay, now the argument of Euclid about the infinitude of primes can be quickly given a demonstration using SageMath if you want, because Euclid argued that there exists infinitely, not actually Euclid. I think Euclid has just incorporated the argument he found somewhere in his Elements book. What he said is that suppose we take any finite list of primes, what happens is that we can still construct another prime number which is not in that list using the fundamental theorem of arithmetic, because the fundamental theorem of arithmetic says that every number can be factored into primes, and we can construct a number which has no prime factor from the given list. That's what Euclid said. Okay, so that problem can actually be, see, these things are all what I call these things are, see, this problem is not actually something pedagogical, but this problem is actually a serious problem, and to get an insight into this problem, we can keep on varying the set and we can see whether this primes 3 mod 4 are overtaking in their size primes 1 mod 4 or not. We can see that. Now, The Euclid's argument on infinitude of primes can actually be seen by taking a set of primes. Suppose that we take the first 100 primes. Suppose we multiply these 100 primes with everything all together, and suppose we add, say, 1 to it. So what happens is that we will see that this is not this is either a prime or a non-prime. If this is a prime, this is not in the given list. If this is not a prime, there is a prime factor for this outside this set, right? The argument can be actually demonstrated. I am not going into that part because we have a few other things to discuss today itself, like the congruent strings. Okay, congruence essentially means that the ring of the set of all integers modulo n. It essentially means that we are supposed to take from 0 to 9, and the arithmetic is also something special there. Okay, let us see how to define that. So for example, Z10, you know that this is 0 to 9. So that's defined using integer mod ring 10. So this is integer mod 10 ring. That's what we are supposed to read. And let us see what is this. So ring of integers modulo 10. So if you really want to see the elements in that, convert that into a list. And in fact, instead of this, we can use Z mod 10. That's also possible. Integer mod ring 10 or this. So how do we access one particular element from this? This is the 0th element. This is the 1th element. So we need to use Z10 not in square bracket but in ordinary bracket. Print Z10. So suppose that this is a modulo 10 ring. So what is the result of 5 plus 5? Result of 5 plus 5 is nothing but it's 10, but it's modulo 10, therefore it has to be 0. And result of 5 plus 6 has to be 5 plus 6 is 11, but modulo 10 is going to be equal to 10. Sorry, modulo 10 is going to be equal to 1. Is that 10 of yes, 5 is the 5th element itself. Now summing it. Let's see if it says 11 or so 5 and 6 sum is 1. So the integer modulo operation is it's correct, and multiplication also we can say 5 into 6 is 30, and therefore that is nothing but 0. So updating the Google document. Now, what are the units in this? So, in Z10, remember that Z10 is a ring, and therefore the operation in Z10 is nothing but integer modulo 10. So, which is essentially taking the sum as the usual integer sum and take the remainder using 10. Now, what are the units in this? GCD with 10 equal to 1. That's what units are. So just take G to be equal to the elements in Z10 U for U in Z10 if GCD of U with 10 equal to 1. One, 3, 7, 9. So, which are essentially the integers in Z10 that are lately primed to 10.
Excuse me, sir.
Yes.
Here we have discussed ring of integers. Is it possible to show that LR5 of n is a group?
Phi of n is a group.
With this code, if we use Sage code, then it is possible to show that it is a group.
So, what do you mean by saying that it's a group? Do you mean Z10 it's the close with respect to, so the conditions you want to verify? Or
Not Z10, phi of n.
phi of n is just a number. It's not a group.
Phi of n that is the set of all prime all integers which are less than n and relative prime to.
So you mean G here, right? See, essentially G consists of all elements below 10 that are lately prime to n, prime to 10. Do you want to say that G is a group? You want to verify that G is a group?
Yes, yes.
So already we have a notation G here.
Yes.
So there are no such built-in commands in that. So what you have to do is that you have to probably verify. There are no built-in commands for verifying if something is a group or not, because the operation itself is not very clear. So G is just a set here. Okay, G is a list here actually. G is only a list here, and in a list you cannot have any what you call group operations. So operation you have to define first, and after defining the operation you need to verify several things. There is no built-in command available for verifying something is a group or not. The only thing is that you can try to find out the group table. Probably you can try to construct if at all you think that something is a group. From that you can probably make out. There is no default built-in command for verifying if something is a group or not, because we cannot specify the operation there. So we need to give the operation, because different sets will be having different operations. So which operation Sage should assume? That's the problem.
Actually, we can convert this list into set.
Even then, which operation Sage should use? How do we specify the operation?
Yes.
Right, because group is something that is the operation also must be present there.
Yes, multiplication. Yes,
but we can of
multiplication modulo 10.
See, we can do all these things in a loop, but it will take some time, because associativity we have to check, multiplication model if you are defining, associativity we have to check, and After that, you need to check this existence of identity. These things we can probably verify using Sage. But for that, there is no built-in already available command in Sage to do all these things. So Z10 is definitely, it's a group. That's a built-in thing. So the units thing is not actually a built-in thing as we have constructed.
Yes.
So otherwise, okay. So otherwise, what you can do is you can define. You can see a command for giving the unit group is there.
Unit group.
Yes. So unit group in the sense that, see, suppose that Z10 you are taking, the set of all units actually forms a group. That's what you essentially want to say, right? Unit group in the modulo ring. That's what you essentially want. So the units modulo. Okay, 1 second. I'll give you that. Just 1 second. I will give you that command, but most probably we have to go into abstract algebra. Okay, I will do one thing. So when we go to this abstract algebra, I will give you, I will try to explain a command using which we can generate, you can find the unit group, which is actually G. Okay, so we are not actually verifying if a given set is actually a group or not, but instead of that, we can directly find the unit group. That's the only thing that's the only thing possible in Sage. Verifying if it's a group or not, that you may have to do it manually, because you already know that inverse X is there or not. See, all these things we can verify. For example, okay, piece by piece we will try to do that. That whatever you want, let us try to do it piece by piece. In the sense that each and everything we will try to verify now, and see if that's useful for see if that's a useful thing for you or not. So, for example, suppose that we try to find the inverse of all the elements. Okay, that we can try to do first. Does all elements in G print for G in G print. Okay, if it doesn't exist, that's actually going to be a problem, because it may throw an error. Okay, maybe what we can do is, okay, let me just try to construct the group table first of all, if possible. So how do we find the group table for G in G? Now print. So what are we supposed to do? Print, no, we need a to looping for so we know that the elements are nothing but, so how many elements are there we need to count. So let us take each and every element we need to loop through for I in range length of G, which is the list, range length of G for J in the same range. Let us try to create the group table first of all, if possible. J in range length of G print I star J, and okay, this is one thing. If I star J in G or not in G, not in, I don't know whether this will work, probably this should work, not in G, we will print multiplication not closed. We will otherwise simply print this I star j. I don't know whether this will actually serve the purpose. I am just trying. So I star j. So after going through one range, after going through one, okay, after that we need to go to new line. So for printing a new line, I will simply use this. Let me just try to execute this code and see. Bracket is missing. Sorry. Sorry. Length of I star j. I should not take I star j. I should take G of 5 star G J. So the ith element and jth element. G I G J. G I G J. What is this? So where am I printing this? For each I, so I want to suppress this new line. So end. So otherwise, what the problem is that each and everything is going to a new line. So end I am giving to be just this. So this is the group table finally. So this is the group table for G, and from this can we conclude that okay, if you really want, you can print I the elements we can print as a line. So maybe we can simply print this I print G of I so for new line. So 1379, maybe here we can give. So what is it we can give here? 1379. To the left of that. Okay, that's going to be a little bit difficult. So if you want to give 1379 here itself, that's going to be a little bit difficult. We need to construct it as. See, otherwise what we can do is that we can construct it as a matrix. So from this table, what we can essentially see is this is closed, that we have already observed, that if G star, if this is not happening, we would have already seen. So the closed we can verify. Now the inverse of 1, probably we can only see that if there is an element, so the inverse also we can see, because 1 is 3.
The composition table, actually you have built.
Yes, the composition table is here already.
The composition table.
Yeah, I think from that we can probably make out, we can display, demonstrate at least.
Yes, thank you very much.
Yeah, that's one way to do that. Again, from the pedagogical point of view. So if you want to use the Sage as a teaching tool, probably you can demonstrate this using, for any set you can do this, for any integer modeling we can do this, and even for some other types of, we will be seeing in abstract algebra, for some other types of this what you call groups like permutation groups, which are really actually difficult to handle in the classrooms, right? Permutation groups, what happens is that the multiplication itself is a little bit difficult. So how do we demonstrate the multiplication? Suppose even if it's a very small permutation group like S3, it's really difficult. Demonstrating the multiplication, that is really difficult. We can make use of SageMath. So we will try to do that in the abstract algebra session. The permutation group
Yes.
also exactly the same thing.
Yes. Yes.
Okay, so let me just update with. I'm updating the Google document with this. So that's right. And one more thing is that the square root function, square function, everything will work. Is something as a square. So that is actually not actually in elementary number theory, maybe in somewhat advanced number theory, that finding out if something is a quadratic residue or not. That means if something is, if some element is x square modulo, x square means quadratic. If some element is x square modulo 10, then that answer also can be given by SageMath using some built-in commands. And one more thing is finding the multiplicative order. That's also possible. Multiplicative order in the sense that, so additive order also you can probably try. Multiplicative order in the sense that, suppose that a to some power in the case of g, if it becomes equal to 1, that's what the least number in such a way that number to that power becomes equal to the identity is known as the order of that particular element. For multiplicative order there is a command, and the additive order also you can probably try. For example, suppose that we take a equal to z is at 10, that's the notation we used. Is at 10, 3 is nothing but 2, I think. That's 3. Now we can find the inverse of it. Means multiplicative inverse here. Additive inverse is just minus 1 by a. Multiplicative inverse, that's 7. Now the multiplicative order also we can find. And additive order, I think additive order also should be possible. Okay, multiplicative order. So for that, just take multiplicative order is 4, which means that 3 to the power 4 is 1 and 3 to no less power is 1. If you take 3 to the power 4, what will happen? 3 to the power 4 is 9, into 9, 81, modulo 10, that's 1. So multiplicative order can be found. Now what about the additive order? So probably that's just order. Oh, sorry. That is nothing but order, because A is in the additive order is 10. So 3 is, it's nothing but it's a generator, because if the additive order is 10, it's going to be a generator, right? So cyclic group, because it's the number of elements is also 10. If the additive order is 10, then it's generator. So we can actually locate all the generators of Z10 like this. Locating generators of Z10. How do we do that? So let us just loop for A in Z10. If A dot additive order is equal to 10, you may simply print A generator. So 1 is a generator, 3 is a generator, 7 and 9 all are generators. So we can locate the generators also by using this technique. Just take the order of the set to be equate with the order of the set and take the additive order. And order, I don't know whether order will work, we can try from. Let me update this also in the Google worksheet. I'm doing everything inside the same cell basically because if some of you want to try these things in the stage cell, if I split it across the stage cell, if I split it across cells, that's not going to work in the stage cell. But if you are working in your own computer, your own installation, you can directly copy and paste this thing across different cells. So it will work. In stage cell, you need to keep everything in the single cell. Now we can create rings of polynomials also. We have already seen that integer mode rings we can create using these commands. Now we can create polynomial rings also over this ring of integers. So over Z. So once again let us define, because for the sake of completeness inside the same cell, let us define Zn once again. Now we are going to declare that x, we know that it's a variable. Now we are going to declare that x is actually a monomial over the ring of all x is a monomial over the ring of all polynomials over Zn. So that we can use x to be a variable. If we create any other polynomial using x, that will be just a polynomial over Zn. So polynomial ring. So we enclose this in this is style in which we define it. Polynomial ring is a 10. You can see what this polynomial ring is. So one variable polynomial ring, we have defined the one variable polynomial ring in which the variable we are going to use is x. One variable polynomial ring with this. Maybe we can see x square plus 2 type of x square plus 1. What is this? You can see that this is Z mod is appearing here. Polynomial Z mod. Now we can perform operations as well. Suppose that we have x plus 5 into x minus 5, x plus 5, type is not necessary. X minus 5, we expect the answer to be x square minus 25, but modulo 10 it has to be x square minus 5 or x square plus 5, because minus 5 is not actually present there. So we get the result to be x square plus 5. To the Google document. See that the factorization of polynomials over this ring is also possible. For example, x square plus 5 can be factorized using the factor command. But this cannot be used in Zn because factor command usually works only in integer modulo, the prime modulus. So for example, if you try factor x square plus 5 I don't think that this is going to work. No, that's not working. Factorization of polynomials over rings with composite characteristic is not. So composite characteristic, prime characteristic only is allowed. This is not implemented. No, not implemented error, you will see. Now on the other hand, suppose that we define Z5 to be equal to, or is it 11 to be the, or better, we can using a single command we can do this. Polynomial over y, polynomial is y, where this is over integer mod ring 11. Now try. Oh, but there is still an error. I should suppress that. Integer mod ring. What is that? Integer. Oh, sorry, that's wrong. Y square plus 5, there is no factorization, but why is it like that? Y square minus 5. Y square minus 5 it's doing. Y square plus 5 it's not doing. Y square plus 5 is what? Probably it's not factorizable there. It's reducible. Y square plus 5. I don't know. Y square minus 5 is nothing but y square plus 11, right? Y square plus 6. Yes, that's there. And in fact, in the same way we can define polynomials over Q cube, same way we can define polynomials over RR, all these things are quite possible. And in between, I wanted to say one more thing, that for performing modular operations, it's not necessary to define the integer mod ring. Directly also we can define. For example, if we define, we can define if you want to work on a single element in one particular ring, finding its inverse, finding its what do you call it? Finding its powers, etc. So you don't have to define it. You don't have to define the integer mod ring first and take element to be that. So instead of that, the mod command is already there. So using the mod command, we can directly define an element to be what you call a modulo element. So suppose that A we define to be 2 mod 11. So this is the way. So it's 2. Type of A. We define a single element. That's it. A square, we can say that it's A square, A to power 2 to the power 4. We know that it's 16, therefore it has to be 5. So 4. That's 5. So inverse we can find minus 1, that's 6, because 6 into 2 is 12, that's 1 modulo 11. And we know the famous Fermat's little theorem, which says that if P is a prime and if a phase between 1 and P, then A to the power P minus 1 is 1 mod P, right? So if we try to demonstrate that thing using Sage, okay, let me just update all these things to the Google document. Suppose that we want to verify Fermat's little theorem. if A is between 1 and P, if P prime 1 less than A less than, and in fact 1 less than or equal to A less than P, then A to the power what is that, P minus 1 is 1 mod P. That's what Fermat's little theorem says is. Now to see that, maybe we can define, let us define P to be equal to 11, say as we have done previously, and A equal to mod 2 P. So what are we supposed to do? We are supposed to take, show that, no, in fact we will show that every element in right, every element in the range 1 to P minus 1 okay, other way, A to the power P is nothing but A. So anyway, we are taking a prime, sorry, we are taking anyway prime P. So I got confused with Fermat's theorem and Euler's that phi theorem. So instead of that, let us take R to be the ring integers P. So this is essentially the same as just R, just Z. Previously we had an integer modular ring. This is essentially the same of that type of R. Again integer mod ring. The same command, integers P, integer mod ring P, all these things are the same. So now we will try to verify this Fermat's theorem that whatever A we choose in this range 1 to P, so let's try to see for A in R, what is A and A to the power P minus 1, just a verification. So let us remove 0 from this. But if you want to remove 0, okay. So there is actually a possible confusion with this command continue. If A is equal to 0, continue, most probably from the our ordinary point of logic, we will think that okay, if A is equal to 0, continue to do all these things. But the command continue essentially means that go back to this A. Okay, go back to this line. Means take another A. If A is equal to 0, take another A. Do not proceed. So continue essentially means that do not go downwards. Okay, that's a little bit confusing, but that's how the programming in most of the programming languages, continue is the keyword used there. Not for going downward, but continue to this for loop. Continue to this line, and again take another A. So we are removing A equal to 0 from here. What I did. Okay. So for Fermat's little theorem we can verify like this. Now one more useful, okay, you can just update the Google document with this. Done. Now one more good result is that even without defining this A to be equal to mod 2 11, we can find the Povet's modulo. So suppose that you want to find 2 to the power 100 modulo 3. Okay, finding 2 to the power 100 is really a huge task even for the computer. But instead of that, if you use 2 to the power mod 3, if you want, that's going to be a very small number, right? 2 to the power mod 3 is going to be a very small number because it's going to be 1 of 0, 1 or 2. So power mod ring command is also there. Power mod is also there for us to try. For example, if you want to try, okay, let us try 2. Suppose that we want to take 2 to the power 100 modulo 3. That's just 1. 2 to the power 100 modulo 4. 0. 2 to the power 100 modulo 7. 2 and so on. So this command is also going to be somewhat useful. This is a dot power mod power modulo. So without defining a to be equal to 2 mod 7, we can do this. Otherwise, we have to define a equal to 2 mod 7, then we have to raise it to 100. That's also, this is equivalent to a equal to mod 7, and then a is equal to 2 mod 7, and then a to the power 100. It's equal to this. So I'm updating the Google Sheet, Google document with this, and with this probably we will stop today. There are several other things in elementary number theory, but my aim is to give actually a brief introduction to almost all basics that probably I have done. And you can the Chinese remainder theorem, if you are familiar with an elementary number theory, which says that a system of linear congruence equations modulo pairwise lately prime modulus can be solved, and we can find out solutions of solutions using the Chinese remainder theorem using the command CRT. But once you are familiar with all these kinds of the basic commands, you can construct your own things, you can proceed like that. Now, the RSA, that RSA cryptography, that RSA problem also can be demonstrated using the SageMath software. I can probably share with all of you a document which I have previously prepared with some of these commands, but maybe towards the end of this workshop with these problems. So if there are any questions to ask related to the topics that we have discussed, you may please ask now, and after that we will conclude. The Google document is already shared, ma'am. Where is that? So that's already here. So once again, I'm copying and pasting that. Okay, thank you very much. If there are any questions, you may please ask. Otherwise, we'll stop. So I think there are nothing. So probably we can meet tomorrow at the same time.
Thank you very much.
Thank you, sir.